Hi, everybody. It's Professor Mitchell, continuing with Chapter 10. Today, we're looking at Section 10.8 on Taylor and Maclaurin series. So we know that within its interval of convergence I, the sum of a power series is a continuous function with derivatives of all orders. But what about the other way around? If a function f of x has derivatives of all orders on an interval, can it be expressed as a power series on at least part of the interval? And if it can, what are the coefficients of that power series? So I'm going to spare you the details of this proof. It's not a difficult proof. It's just kind of boring. All right. But it's not hard. Assume that f of x is the sum of a power series about x equals a. That is, f of x is equal to the sum n going from 0 to infinity of a sub n times x minus a to the n. By repeatedly differentiating the series term by term and evaluating the derivatives at a, we can show that if f has a power series representation, that power series must be the first one given here. All right, so this is a definition. Let f be a function with derivatives of all orders throughout some interval containing a as an interior point. Then the Taylor series generated by f at x equals a is the sum k equals 0 to infinity of the kth derivative of f at a over k factorial, so that's the coefficient, times x minus a to the k. So the first few terms of that series are f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared, and the general term is the nth derivative of f at a over n factorial times x minus a to the n, and so on and so on. This is an infinite series. A special case of a Taylor series is called the Maclaurin series. This is simply a Taylor series at x equals 0. And that is the sum k going from 0 to infinity of the kth derivative of f at 0 over k factorial times x to the k. And you can see the first few terms and the general term of that series here. All right, if you cut off a Taylor series at a particular term, what you get is called a Taylor polynomial. If you think back, let's see, I guess this was maybe the last section. I don't know, it was a couple sections ago. We started the section with looking at f of x equals sine x, and then a few polynomials, which did a better and better job of approximating sine x near x equals 0. So now I'm ready to tell you that those those polynomials were Taylor polynomials. Let f be a function with derivatives of order k for k equals 1 through an integer n in some interval containing a as an interior point. Then for any integer little n from 0 through big N, the Taylor polynomial of order little n generated by f at x equals a is the polynomial p sub n of x equals f of a plus f prime a times x minus a plus f double prime a over 2 factorial times x minus a squared, all the way up to the nth derivative of f at a over n factorial times x minus a to the n, and it stops there. This is not an infinite series. This is just a polynomial. All right, and we are already ready for examples. And once we've gotten through these examples, that's going to do it for section 10.8. So switching over to the tablet. All right, first we're going to find the Taylor polynomials of orders 0 through 3 for the function f of x equals tangent x at a equals pi over 4. So in order to do that, we need the first three derivatives of tangent x, and we need to evaluate those at pi over 4. So the first derivative of tangent x is secant squared x. And when you evaluate that function, actually, okay, just a sec. When you evaluate that function at pi over 4, let's see, the secant of pi over 4 is root 2. Root 2 squared is 2. I almost forgot that I really need to start with f of x. Because the very first coefficient is going to be f of pi over 4. And the tangent of pi over 4 is 1. Okay. So now we can continue. F double prime of x is the derivative of secant squared x, which is 2 secant x times the derivative of secant x, which is secant x tangent x. So that's going to be 2 secant squared x tangent x. Excuse me. And when we evaluate that function at pi over 4, we get 2 times root 2 squared times 1, which is 4, right? Okay. I'm very happy we're not going past 3. Okay, so I'll use the product rule on this. We'll make this f, we'll make this g. All right, so the first times the derivative of the second is going to be 2 secant squared x times secant squared x, plus the second times the derivative of the first. Well, the derivative of 2 secant squared x, let's see, is 4 secant x times secant x tangent x. And then we have this other tangent x here. Okay, I'm pretty sure that's correct. So that's 2 secant to the 4th x plus 4 secant squared x tangent squared x. And when we evaluate that function at pi over 4, we get 2 times root 2 to the 4th plus 4 root 2 squared times 1 squared. Let's see, root 2 to the 4th is 4. So this is 2 times 4 is 8. Root 2 squared is 2. So this is another 8. And f triple prime at pi over 4 comes out to 16. All right, so we have these as our coefficients of the Taylor polynomials. All right, so P0 of x, that's a degree 0 polynomial. In other words, a constant function. That's just f at pi over 4, which is 1. The first degree Taylor polynomial is f at pi over 4 plus f prime at pi over 4 times x minus pi over 4. This pi over 4. I said it right, wrote it wrong. Now we can do that, right? Okay, so f at pi over 4 is 1. F prime at pi over 4 was 2. Okay, so my first degree Taylor polynomial is 1 plus 2 times x minus pi over 4. Second degree is going to be f at pi over 4 plus f prime at pi over 4 times x minus pi over 4. plus f double prime at pi over 4 over 2 factorial times x minus pi over 4 squared. All right, so we already have the first two terms. 1 plus 2 times x minus pi over 4. We know that f double prime at pi over 4 is 4. So let's just make a note there. That was 4. 4 divided by 2 factorial is 2. So this will be plus 2 times x minus pi over 4 squared. And then finally, P3 of x is going to be f of pi over 4. I thought about writing this a lazier way, but I don't want to confuse anybody. So f double prime pi over 4 over 2 factorial x minus pi over 4 squared. Unfortunately, I am going to run out of room. Plus f triple prime pi over 4 over 3 factorial times x minus pi over 4 cubed. All right, so we're going to have to, oh dear. Okay, well, just note that there's my first answer, my second answer, my third answer, and now I have to erase at least my first answer in order to get the rest of P3 of x. Okay, so continuing from the bottom, we have 1 plus 2 times x minus pi over 4 plus 2 times x minus pi over 4 squared. Okay, now f triple prime at pi over 4 was 16, right? So this here is going to be a 16. So the next coefficient is going to be 16 over 3 factorial. 16 over 3 factorial is 16 over 6, which is 8/3. So let me just put a note here explaining where I got that. This is 16 over 3 factorial times x minus pi over 4 cubed. And that would be your third degree Taylor polynomial. So as kind of a fun side exercise, I'm not going to actually do it because you've seen me do something like it before. Take your graphing calculator and graph the function f of x equals tangent x, and then compare the graph of that function to some or all of these graphs near x equals pi over 4. You should find that they do a pretty good job of approximating the tangent curve near that point. All right, next example. In this problem, they wanted us to find the Maclaurin series. Remember, that's just the Taylor series about x equals 0 or about a equals 0. Okay, so for this, what you really need to do is start with the function. And then evaluate the function at 0. So that comes out to 0. And then take enough derivatives evaluated at 0 until you see a pattern in the coefficients. All right, so by the product rule, the derivative of x e to the x is x e to the x plus e to the x. And at 0, that is equal to 1, right? Second derivative is going to be another x e to the x plus e to the x, but then the derivative of e to the x is another e to the x, so that's 2e to the x. And when you evaluate that thing at 0, you get 2. All right, well, that's a nice simple pattern. Hopefully it holds up. Let's try one more derivative. So the derivative of x e to the x is x e to the x plus e to the x. The derivative of 2e to the x is 2e to the x. So I started with 1e to the x. I picked up 2 more e to the x's for a total of 3. Okay, and just like I was hoping, the third derivative of f at 0 is 3. So remember so why don't we do this? And actually all I need really is the nth derivative at 0. It looks like the nth derivative at 0 is n. Okay, because the formula for the Maclaurin series is the sum n going from 0 to infinity, nth derivative of f at 0 over n factorial times x to the n. And now that we have a nice formula for the nth derivative of f at 0, we can just fill that in. The nth derivative of f at 0 is n. And n over n factorial is just 1 over n minus 1 factorial, isn't it? So the Maclaurin series for the function x e to the x. Uh-oh, wait a minute. Darn it. Okay. I'm going to have a little problem writing it that way because if this starts at n equals 0, in the very first term, I'm going to have a -1 factorial, which is undefined. I think that I can actually get away with starting it at n equals 1. I'm going to double check that. Okay. Because the first couple of terms of the series, let's do this on the next page, are 0 plus 1x plus 2 over 2 factorial x squared plus 3 over 3 factorial x cubed, which is x plus x squared plus x cubed over 2 factorial plus x to the 4th over 3 factorial. Okay, so if I start this series at n equals 1, the first term is going to be x over 0 factorial, which is x. The second term will be x squared over 1 factorial, which is just x squared, and that will work. Okay, so this is my Maclaurin series for f of x equals x e to the x. And by the way, in the next lecture, which is a combination of sections 10.9 and 10.10, I'm going to show you a different way to find this Maclaurin series, which you may find a lot easier. All right. Okay, last example is in 2 parts. They want us to find the Taylor series for this function about the indicated point. So again, this is just a matter of taking derivatives until you see the pattern. Remember to always start with the original function. F of x equals 2 to the x. F at 1 is 2. All right, now who remembers how to find the derivative of 2 to the x? Okay, from way back in chapter 7, I don't think we've used it all that much since. The derivative of 2 to the x is 2 to the x times natural log 2, which means the derivative at 1 is going to be 2 times natural log 2. All right, continuing until we pick up a pattern, f double prime at x. So the derivative of 2 to the x is once again 2 to the x times natural log 2, but we have this other natural log 2, which just comes along for the ride from the constant multiple rule. So that's going to give us 2 to the x times natural log 2 squared. And when you evaluate that function at 1, you get 2 times natural log 2 squared. All right, I'm starting to suspect that I know what the pattern is. Let's check one more. Derivative of 2 to the x is 2 to the x natural log 2. And we have this other natural log 2 squared. So you put them all together, you get 2 to the x times natural log 2 cubed. And that function at 1 is equal to 2 times natural log 2 cubed. So it looks like the nth derivative of f at 1 is 2 times natural log 2 to the n, right? Okay, so the formula for the Taylor series is the sum n going from 0 to infinity, nth derivative of f at a over n factorial times x minus a to the n. And in this case, the nth derivative of f at a is 2 times natural log 2 to the n. So that's going to give us 2 times natural log 2 to the n over n factorial times x minus 1 to the n, right? Because a is equal to 1. All right, that is the Taylor series about a equals 1. All right, and finally, we have f of x equals the square root of x plus 1 about a equals 0. So this is really a Maclaurin series. So we'll start with f of x. And I'm going to write it like this because we're about to start differentiating it. F at 0 is equal to 1, right? The square root of 1 is 1. So now we take the first derivative, and that's going to be 1/2 x plus 1 to the negative 1/2. And when you plug 0 into that thing, whoops, you get 1/2 times 1 to the negative 1/2, which is 1/2. All right, now starting with this second derivative, okay, again, using the power rule, the negative 1/2 is going to come down. And I have a little trick up my sleeve. I am not going to multiply 1/2 times 1/2 and get 1/4 because that might obscure the pattern. Instead, I'm going to leave it just like that. And the new exponent is negative 3/2. And when I plug in 0, I am left with negative 1/2 times 1/2. So this is kind of a curious pattern. Might need to go past the third derivative for this one. Okay, well, for the third derivative, you bring down the negative 3/2. So that's going to flip the sign back to positive. Something here starting to look familiar. It's come up a couple times in this chapter. Okay, so the third derivative at 0 is 1/2 times 1/2 times 3/2. All right, let's do one more. That would be the fourth derivative. Okay, well, if you bring down the negative 5/2, the sign flips back to negative. Okay, remember this odd number factorial thing we've talked about a couple times before? It looks like that might come up here. All right, and the fourth derivative at 0. I don't know why I put that Roman numeral 4 in parentheses. Doesn't really matter. Okay, so it looks like we have a pattern for the nth derivative at 0. So let's talk about the easy part first. Well, there's actually two easy parts. First of all, it has an alternating sign, at least starting at n equals 1. So most of the time we want it to be negative when n is even and positive when n is odd. So what does that is -1 to the power n plus 1. And we also want 2 to the n on the bottom, don't we? Okay, but then upstairs we want this odd number factorial. So just to make sure that I have the pattern, which really starts at n equals 3. Okay, so in other words, I want to see what is the relationship between second derivative, the last factor is a 1, the third derivative, the last factor is a 3, the fourth derivative, the last factor is a 5. All right, well, those numbers are going up by 2s, so you know my trick for that. Start with 2n, so that would give me 4, 6, 8, 10. But what I really want is 1, 3, 5, 7, right? Which means I want all of these things to be 3 less than 2n. Okay, so what I can do upstairs is just write 1 times 3 times 5, et cetera, up to 2n minus 3. Now, in previous sections, we spent some time finding sort of a closed form for that expression, and that's because I think in every one of those cases, we were using the ratio test to figure out where it converges. We don't have to do that this time because it didn't ask me where it converges. So we're not going to do any ratio tests. So I think I'm going to leave it just like that. Okay, so now to write down the answer, it's going to be, okay, Taylor series is the sum k, n going from 0 to infinity, nth derivative of f at 0 over n factorial times, well, we can just write x to the n here. Again, this is really a Maclaurin series. Okay, and we have that ugly expression for the nth derivative at 0. Okay, so we have the n factorial that's built in here. And then the expression for the nth derivative at 0 is -1 to the n plus 1 times 1 times 3 times 5 up to 2n minus 3 over 2 to the n, right? And now I just need to tack on this x to the n. Whew, okay, so that was kind of a workout, but that is the Taylor series that we're looking for. All right, and that's going to do it for section 10.8, and I'm really excited about in the next, I don't want to call it section because it's going, I like to combine sections 10.9 and 10.10, so let's just say in the next lecture, I'm going to show you some nifty applications of Taylor and Maclaurin series. So until then, have a great day, and we'll see you next time.